the surface plot will look like. We called it a surface plot. And we have taken the parameters W, B, and cross entropy of the zeroth class. And we have defined a color map, which is taken as plasma. There are different color maps defined in Python. You can search and replace it by your own. So age color none. So the age is not colored here. And define again title, labels, and red label. And then the second plot defined by AX2. So the second figure window of the subplot. So 1 to 2 means the first row, 2 columns, and it is on the second place. So last two will be called as that this subplot will be on the second place. So it is here for the one class cross entropy. So again, we have defined the parameters, weight, biases, and the cross entropy of one class and color map at each color nut. Again, the title and labels defined here. So this is how the cross entropy for two class of zeroth class and for one class will look like. These are the mirror image of each other, if you can see, and these are also convex because binary cross entropy in logistic regression behave like a convex function.
Hello? Hello?
The second cross. Hello? Yes, ma'am.
हाँ रिंकी, यू आर नॉट ऑडिबल. बीच बीच में वही आवाज तो जा ही रही है. चैट में भी लिख के आ रहा है. आई डोंट नो व्हाट इज द प्रॉब्लम टुडे, वेदर इट इज वेबएक्स और
No, I think it's Webex problem. All sessions have problem.
voice is breaking.
I will repeat this.
So don't worry, participants. What we can do is we will share these codes also in your Canvas material, so you can try to run it, and if there is any doubt, you can WhatsApp it at that point. So now we can just continue with the session.
Okay. So this is how you can see the codes. The all code file will be provided to you, so you can try on your own. Now the second loss function is mean square error. So we will plot a mean square error curve, that how mean square error will look like in 2D. So first we will import the NumPy library and Matplotlib library, and we have set a target value which is 3.0, which is 3. So y hat is the predicted values of 1000 evenly spaced values between -2 to 8. And we have defined mean square error as MSE here. So it is y true minus y hat to square. So it is the mean square error for this. And again, we have defined our plot values and labels and all title and all. So here you can see that how mean square error will look like. So it is a convex function, a strictly convex function, and minimum at here y hat equal to y. The global minimum is found here. So this is interpretation in 2D, and we will look here for 3D. So for 3D, we will again import the axis 3D for 3D plot and generate 100 evenly spaced values, and y also 100 evenly spaced value for y predicted and true values of 100 evenly spaced. And then we will create a mesh grid for the 3D plot, and again compute the mean square error loss, which is y minus y hat to the square. And this is all same things for the figure we have taken. So this is the 3D visualization of the mean square. You can see the similarity convex function, and it for its global, which is a straight line where y equal to y hat. It is mathematically interpretable also, that whenever is y equal to y hat, line. find its global minimum. So for that line, it will find its global minimum. So that's how the binary cross entropy, category cross entropy, and mean cross entropy will look like in a simplest way. But in a neural network, it will get complexity through the computations and activations. So the surface will change. So we have taken a function to show you the surface of neural network loss, how the surface of the neural network loss will look like. So that's how the surface of neural network loss or the machine learning model loss will look like. There is not a convex surface. There is a non-convex surface with a multiple minimas, multiple saddle points and valleys. So that's why it is a complex surface with local minima saddle points. We have taken a function which is sine 3x cos 3y plus 0.5x square plus 0.2y square. The surface belongs to this function, but it is an inference. Inference uh, it, uh, it is more easy, but in machine learning, there are many that does not is defined here through surface product self and if I type it here, function is find the surfaces and how. So now we will see how non-convexity will generate in the cross entropy, binary cross entropy function. So for this, we will use the logistic model. So for this, we have defined a random classification data of hours of studies and pass or fail target value. So X is hours of study by the student, and Y has the 0 and 1 value. So 0 is for fail and 1 is for pass. And these are the libraries and import math, random, numpy, and plt. So this implementation demonstrates how logistic regression minimizes the binary cross entropy loss using gradient descent. The key objective is to provide a both computational and visual understanding of the convex nature of the binary cross entropy loss function in logistic regression. So we have defined here the sigmoid function. Define sigmoid, Z is a parameter, input parameter. So we have define a definition of sigmoid function here, which will return whenever we call sigmoid, it will return 1 upon 1 plus e to the power minus x, whichever the input we provided. And there is a prediction function. So for the prediction in logistic regression, we will take sigmoid of wx plus v, which is defined here. So the input parameters are x, which is input data, W weight parameters, V is bias, and then the definition of compute loss, which is X, Y, W, B as taken as input parameters. M is equal to length of X, which will provide us the number of samples. Loss is 0, and for each sample, the loss is computed and add up. So first, y hat is the predicted value, so it will call the prediction function. This predict will call this function, and it will return the sigmoid of these values for the first sample. Then loss will compute it for the first sample using log function, using binary cross entropy function, and again for the second sample this thing will do. Then for all the sample this thing will do, and loss will add up for all the sample, then it will return loss by m. M is the number of samples. So this is the average loss of these samples. Now we will define a second definition of the train logistic with path. So whenever we call this definition by providing the input x and output y, uh, it will compute the logistic regression with path, and learning rate and epoch will have the default value set 0.101 and 100. So we have and initialize and biases by m dot uniform will on the uniform distribution between -2 to 1. And exam and then always updated by the gradient descent, then the updated value will also inserted in the path array. So path is an array taken up on the point of x which is updated from starting to end. So for from the start folks are rented here, it will run from 0 to 99 in Python, but so 100, so 100 is so it will from 100 for 100 is the gradient of loss with respect to the for bias, and we have initialized it with 0. And for I in range of m, so range of a number of samples, so it will run up for every sample. Y hat will provide the predicted value, and for this, dw will take the gradient of with respect to weight, and dv will take the gradient with respect to bias, and it will add up for every sample. So these will store the sum of gradients all over data points and total gradient for current epoch. So it is happening in one epoch only. So after this, we will update the weights and biases using gradient descent. The formula is W equal to W minus learning rate multiplied by gradient. So after this path dot append, so the dot append function will add up the second value which is updated after WB in the path array. So after this, the all things will run for the number of epochs, and these all things will happening in this definition. So after the all epochs have run, then we will print if epoch divided by 10 remainder 0. That means we will print result for every after every 10 epochs, like for 10, then 20 and 30. So it will print epoch, and for the number of epoch, the losses, compute loss x by wb. So it will compute the loss for after every 10 epoch the computed weights and biases, and dot 4f will provide the decimal number up to 4. So it will return w weights, biases, and path. Array path is an array. So whenever we call this definition train logistic with path, it will return us three parameters: weights, biases, and an array of weights and biases. So which is path here. So here we have WB path will return by this train logistic with path x and y we have already defined here. So we provide input as x and y for this definition. Here we have only defined the definition. Here we call the definition. Then it will return as these three parameters, and we will print the final weight and final bias after 100 epochs. So these are the things for epoch 0. This is the loss. Epoch 10, 30. This is the loss which we have printed by this line, and the final weight and final bias is this. So now we will convert our path array to a numpy array for the convenient to computation. So it so array will convert it into a numpy array, and w values are and v values are. So path is an array now. Every entry of path has two coordinate, x and y coordinate. So this thing will take the x coordinate and this thing will take the y coordinate. So W values are on the x coordinate and V values are on the y coordinate. So it will assign like this. And W range, we will provide a range of W and Y's to create axis. So we will take a minimum of from all W values, we will take minimum of W values and -1 of this, and maximum of W values +1. So all W values and V values will be come up in this range, and we will take 100 evenly spaced values in this. So after this, we have create a mesh grid again, and Z. So Z is WX plus B. So the dimension of Z is like W. So NP dot zeros like will create a array like W of zeros. So it is an array which has same dimension as W, but the entries are zeros here. And for I in range of W shape 0. So for the rows of W, the I loop will run. And for J in range of W dot shape bin, so for the columns of W matrix, the J loop will run. So Zij will compute for every entry of WB. So compute loss is X, Y, Wij is entries of the W matrix, and Bij is the entries of the Ys vector here. So that's how we will compute loss, and the weights and Ys are X's for the 3D surface plot. So again, we have defined the things for the 3D surface plot. Here, the new thing is that thing. So AX dot plot will plot W values, V values at X and Y values. And for the Z value, we have taken for WB in path. So it will take values WB in path from the path array. So we have WB from path array, and it will insert the parameter in this compute loss. X and Y are already defined. So it will return the loss for every entry of the array. How the J value is computed for the surface, and again the title and labels are defined. So, and this is a subplot for 1 to 1. It will represent at first place. So this is the binary cross entropy loss surface for logistic regression. It is a convex surface, and again we have plot a contour plot by ax2 dot contour will create a contour plot for surface. We have taken plot underscore surface. So it will create W, B, Z. Labels are 50. So 50 labels means these 50 lines for every function will take up, and color map. And again, we have plot the path of gradient descent also. So for this descent, color descent color is red for yellow. We will look further. So we again sigmoid function, and X W we define assume that a model have taken multiple sigmoid function here for on Wx plus b. So if you remember, in a neural network, first linear transformation Wx plus b has done in first layer. Then the sigmoid function, activation function, sigmoid and other activation function are applied. Then again the bias and weights will add up, and again sigmoid function will add. So how we have applied multiple functions is now for this definition. So whenever we call model, it will provide us the output after applying multiple sigmoid function, and we biases are same for every sigmoid for the simplicity. And binary cross entropy have defined here y hat and y epsilon for taken for numerical stability. So it will return the binary cross entropy loss, and x data y data is same as above. So we have created a grid over weights and biases. We have taken W values between -10 to 10 and bias, and again create a max grid. We again define here as a zero matrix like W dimension. So for I in range of W dot shape 0, it will cover the rows of W matrix. It will cover the columns of W matrix. And loss is initialized by 0. So for xi, yi in zip of x data, y data, for xi, yi, it will take first entry of for I equal to 0. Then y hat equal to model y hat equal to model will call y predicted value will computed for this definition. So model will call x w v. So it will take from here, and it will return the after multiplying after applying multiple sigmoid function. So loss will compute for this y hat, and it will again add up for every entry in this data, and Zij will compute it, which is the loss value, and divided by length of x data for the average loss. And we have plotted the figure here. So this is the surface plot of binary cross entropy after applying multiple sigmoid function. See that if we apply sigmoid function single time, then the convex. But if we apply sigmoid function uh, multiple times, so we will get it in a non-convex manner. So it is a non-convex surface. The intent is the non the in this yes, you will find any any So we will start for the non-convex surface function for gradient descent method. So we have taken a non-convex function which is defined as here. So it is produces a complex 3D surface with multiple minimas and saddle points, and we will run the gradient descent with momentum, EDA grade, RMS prop, and ADAM here. So again, we have imported the libraries and define the function here fxy. Whenever we call fxy, it will return us this function. And so here we have defined the gradient of this function. So whenever we call the grad function by giving the inputs xy, array, convert it in numpy array of partial derivatives of this function, which is the gradient values. Now we will define the optimizer definition to use on this function surface. So here is the definition optimize, and the parameters for the definition is method, which will the method gradient descent, gradient momentum, Adam and all, and learning rate and steps. Steps are iterations here, 100 iterations, and learning rate. These are the default values already defined. So main parameter is method here. So we have first initialized the starting point. I have taken it as 0.0 and minus 0.5, and we have defined an array of trajectory. So TRJ will contain the path of this for each method. It will contain the path of each method. So external copy will copy this value in this array. So first entry of this array will be the initial point. Then again, whenever we updating this by any method, it will append this in this trajectory array. So we have defined the initialized variables for optimizers for stretch. So we have defined a velocity for momentum, and every parameter, every variable has the dimension like x. So np dot zero like x. So for initial values, these are the zero values. So it will create a zero array of like x dimension, and m also first moment for Adam, and v hat the second moment for Adam, and epsilon, which is e to the power minus 8 to prevent division by 0, and g is the accumulated gradient square. For if you remember in ADA grade and RMS prop, we have taken the square root of gradient accumulated gradient square. So we have defined this at capital G. So for initially it is 0, and parameters for Adam beta 1 and beta 2 are default values are 0.9 and 0.9. These are empirically tested, and these are the best values of these parameters. And momentum has defined at beta, which is 0.9. So we now process the optimization loop. So for t in range of 1 to steps plus 1, steps are 100 defined. So it will, because in Python, the range function will run through. If I define 1 to 100, it will run to 1 to 99. That's why plus 1 has been taken here. So it will run from 1 to 100. And G will take the gradient at current position. So G is gradient of x0, x1. X has two values, x and y, x coordinate and y coordinate. We have defined. So 0 will define, x0 will define x coordinate, x1 will define y coordinate of the initial point, which we have defined. And grad will compute the gradient of on that point, and it will assign to G. So now G is our gradient at the initial point. So if now here we have taken method different method. So by if conditional statement, so if equal to GD. So method is come from this definition. So if defined the parameter for optimized definition at G, this definition at GD. So this is the simple definition of GD. It will be equal to x minus multiplication And else if the method is momentum, then the momentum formula is defined here. And else if method is EDA grade, then the EDA grade formula is defined here, because first is 0. So accumulated gradient descent will add up again and again. Again will updated by this formula. Then again gradient will computed at the updated point, and again it will add up. And if you remember the formula, x equal to x minus gradient divided by E is the current divided by gradient, and capital G is the accumulated gradient. So this is for EDA grade. And for RMS prop, we have decaying average of a square gradient. So we will give beta which is 0.9 is multiplied by G, and 1 minus beta for square gradients. So the decaying average of square gradients has been taken from this line, and this will update the x point from the RMS prop definition. So again, the Adam definition has been defined. You can see the formulas of the RMS prop and Adam and these optimized. Then can we compare it by this coding? This is a simple mathematical functions which we have inserted in a Python manner. So nothing new here. So again, Adam function is defined here, and this function dot append function will add the updated point x dot copy in the trajectory array. You remember we have defined the trajectory array here. It has multiple points, updated points of x. So if let's say we have run the optimized definition here, I provide the method momentum. Then the momentum will call from here, and x will update by this definition. Then we will come here. Then the updated x will add up in this trajectory. Then again we will we will on this momentum, again x will add up, x will update it, and again the updated x will add up in the trajectory array. That's how this will do for the path of the method, each method. So it will return the trajectory array as a numpy array. So it will, whenever we call the optimized definition, it will return the numpy array of trajectory. So to show this function on a surface, we have defined a dictionary for the color mapping of optimization methods. So and for this loop, we have created a dictionary methods. So if this methods equal to GD key value, methods have GD key value, dictionary has a key value, and uh, an inference regarding to it. So if there is a GD key value, it will take the red color in the plot. If it is as a momentum key value, it will take the blue color in the plot. Same for others. So run the optimization for each method and store the resulting trajectories. So it will create a dictionary here. So how it will create a dictionary? Let's see. Name is the key value in dictionary. Look like this. First, it is a key value, and the value regarding these can be a string, can be an array, can be a value, anything. Here, there is an array regarding each method. So for GD method, there is an array of the updated points by the GD. For momentum method, there is an array of the updated points by the momentum method. That's how it will create a dictionary of trajectories. Name will come from where? Name will come from here for name in methods. So it will take here from name in methods. So in methods, we have 5 key values. So it will take the first key value GD for name in methods. For GD in methods, it will create dictionary. GD is a key value. Then for colon in dictionary, we have colon for every key value. So here are also optimized name will call. So optimized name will call and optimized GD will call, it will return us the trajectory of that particular method. So for every method, we have the array of the path in this trajectory dictionary. So now we have all things sorted. Now we have to plot it. So X, Y, and Z are computed here, and define a figure window here for and for subplot position 3D for the 3D plot. And to plot surface, we have provide the command plot underscore surface XYZ, and the color map has been taken pool bar and alpha is 0.7. So for name, now for each method, we have to plot each method in a single figure. So for name, trajectory dot items. So what trajectories dot items will do? Trajectories is a dictionary here. So we have two values for each. First is a key value, which is here, and second is the path array in this dictionary. So name for the key value, and trajectory will take the path array in trajectories dot items. So ax dot plot will plot the trajectory colon 0. It will take the x coordinate of all entries x colon 0, and trajectory colon 1, it is an array. So it will take all the y coordinates of all entries. So I think you understand, 0 for the x entries and 1 for the y coordinate. And f x y will compute it from here for each entry of the path array, and color will call method's name. Color will call method's name, which will compute it from here. So name, if we are calling only one thing, then it will take only key value. So color is method's name, will take only key value GD or momentum, and the label is name dot upper, means for name has been taken from this. For GD, label will define GD, and dot upper will allow to the labels from upper side. So it is on upper side. So again, we have said title, label, and reasons. And again, for second subplot, we have defined the figure window AX2 and taken XYZ entries. And for name, trajectory and trajectories dot items. So we have two values in this dictionary. So all two values are taken from this dictionary, and ax2 dot plot will take x coordinate, y coordinate, and color and label. It is path. So it will take all x coordinate, y coordinate for each particular method. And ax2 dot scatter will create a single point dot scatter. So it will 0, 0, 0, 1 is the start point. 0 will create the x coordinate of the start point. 1 will show the y coordinate of the start point. And trajectory minus 1, 0 will show the end point. So the minus 1, 0 is the x coordinate of the end point. Minus 1, 1 is the y coordinate of the end point. So, and these are the labels again. And this is the surface, a non-convex surface, which is the saddle point and the local minimas, if you can see, and global minima also. So if we run all these methods here from starting from here, the momentum is overshooting all the methods and reaching faster than to a local minima than others, because we have taken critical point. So that's how the method works by the initialization. Initialization affects the convergence of all the methods. If I take a point here, then all methods will converge for this critical point. So because it is a non-convex surface, the minimas, local minimas and saddle points are nearer. That's why everywhere we can take any initial point that will converge to the nearest local minima, or stuck in the nearest saddle point. So this is an inference of these methods, how these methods will work on a surface, but in practical and real world implementation is for neural network of these methods. So we will see the practical implementation on neural network for a multi-class classification task on mobile price dataset. So mobile price dataset is a dataset which has the features of a particular phone specifications and a target label basis representing the price range category. It is a 4-class classification data. So it aims to predict the price category based on the given features. We have imported essential libraries, pandas, numpy, matplotlib, scikit-learn, and tensorflow keras. Scikit-learn and tensorflow keras are the important library for the machine learning. It will allow us to import data and handle the data, normalize the data, and create model for create neural network model for us. These machine learning tasks will provided by these libraries. So here we have import all this pandas for reading the data file and create a data frame, numpy for numerical computation, matplotlib for the plot, sklearn.model selection will import train test is split which will split the data set in a training and testing parts, and standard scaler will normalize the data set because large range features can affect the training of the data. And import for TensorFlow from Keras, we will import sequential for building a model. Sequential will allow us to build a model which will stack the layers one after other. And again, we have import dense. Dense will command for the fully connected layer. And from TensorFlow.keras.optimize, we can import any optimizer we have defined earlier directly, like from these names, like import SGD will import the stochastic gradient descent optimizer, and from tensorflow.keras.util import to categorical. This command will allow us to encoding the labels to do convenient mathematical computations for the prediction function. Like we will see further how to categorical will work. So here we have created a data frame from PD pandas library. So this data file will be provided to you. You can simply upload it from here. So here this is not connected to a runtime. You can see a arrow sign here on the top left corner. By tapping it, you will upload the file and copy the path of, and then file can file will be shown here, and try to copy the path and paste it, the copy path. Then the file can be read by this command, and df.head will show you the first 5 entries of the data. So these are the features, and this is the price range. Now these price range between class 0, 1, 2, and 3. These are the 4 class, 0 class, 1 class, 2 class, 3 class. So how to categorical work we will see here. So for to train, we have to drop the target column. Target column is price range column. So don't have to train it. So it is a df.drop will drop the price range column. X is equal to 1 across the rows. That means for every row, the price range column value will be dropped. Dot values will convert into a numpy array, because here these are not a numpy, so dot values will convert it into a numpy array. And while is two categorical, so price range dot values are here 0, 1, 2, and 3 only. And df price range dot values will convert it into a numpy array, and two categorical will convert into a one hot encoding. Like if my sample will connect it to a one class, like one zero class, the one zero class, one class, two class, three class. These are the 4 classes. One class, then it will provide one to the second index of this array. It will, if it will connect it to the second class, then it will provide the index to the third index. Because in Python, each entry starts from 0. So that's why it will convert to the fourth class, which will be represented as 3. So it will provide 1 to the fourth index. That's how the one word encoding will done. And if you remember the categorical cross entropy, we computed by this that all entries are 0, um, except the two classes. So the two classes 1 here, so all entries are 0. Two classes 2 here, so all entries are 0. So this conveniently compute the categorical cross entropy loss. That's why two categorical will used in this task. And again, train test split has been done. X train, X test, Y train, Y test. And test size is 0.25. So the 25% data will provide for the X test and Y test. Y train, Y test are the target vector of the data set. Random state will allow the distribute data randomly, and we will print the SQL dot shape will print the shape of the data. So 1500 data 1500 data points are in the Excel main set, and the 500 data points in the text set. So now we will create a neural network architecture using Keras TensorFlow. So we will build a fully connected feed-forward neural network. So first we will import sequential, and second we will import dense and input from the TensorFlow Keras. So all machine learning things will do from the TensorFlow Keras. So we will define the definition build model. It has no parameters here. So model is sequential. Model will be sequential, like all layers will define here. It will take up in this manner only. Like first layer will be this, second layer will be this. Sequential will allow us to do that. So model dot add in model, first we will add an input layer which has the shape as the features. So x dot shape one are the number of columns in x data which are features of data. So input layer has neuron as features, and model dot add it will again we will add a dense layer of 64 neurons with activation ReLU. In a hidden layer ReLU works well, so we have taken hidden ReLU. And model dot add again we have taken a dense layer of 32. Again we have taken a dense layer of 60. So it is a feed forward connected sequentially neural network. And model dot in last output layer, because we have 4 classes here, so we have taken 4 neurons, and activation is softmax, because in for multi-class classification, the softmax is feature. So it will return as the model. Model is this. So it will take these all layers and add up in this, and it will return as the model. So now we will call model equal to build model definition will call, and it will return the model by for this 4 layer. And optimizer is SGD. We have already imported SGD from TensorFlow. Keras optimizer import SGD. So that's why SGD learning rate we have defined at 0.001, and it will come model.compile will define the mechanism of neural network, how what is the optimizer will be taken, what is the learning rate will be taken, what metrics should be taken, so what loss will be taken. So model.compile will take the optimizer of as this optimizer. SGD learning in here, and loss is categorical cross entropy because it is a classification in problem, and matrix is accuracy here to monitor. And now to train the model dot fit function will proceed. Model dot fit function will on a train data x train, y train, epochs are 10, batch size and verbose equal to 1 allow us to visualize the training. So for you can see here for first epoch, second epoch, we have trained here for 10 epochs. Here we have taken SGD optimizer, so the accuracy is not as much because SGD optimizer is slow on neural network. So history is a class which is defined already in a TensorFlow. So this is defined already. You can see after clicking on the history. So yeah, you can see here the all things. So by clicking on everything which is defined already in the library, you can see the full information of this thing. So this is the history definition. This is already defined in Python. So here we have train the model. Now to plot it, we have defined plot, and history.history is now a dictionary which has the matrix. History is a class, and history.history is now a dictionary which has the matrix like loss and accuracy and all. So by this we are extracting the loss from this dictionary and provided and plotted and provide the label as SGD loss and training loss, and we have also plot the training accuracy from with the same extracting the accuracy key value from the history.history dictionary and plot it. So these are the plot from the SGD optimizer. So now we have to test our trained model by from sklearn or matrix. We have import classification report and confusion matrix, which are crucial for testing our model. So these are already defined in sklearn library, and import seaborn as SNS. SNS are is imported to create a heat map, which will be shown, and by predicted probability will compute the probability distribution over all classes. Model.predict function will test the model on test dataset, which is X test, and by predicted labels will take the maximum probability will provide to which class, and it will return that class to this variable. So arguments will test that which class has the maximum probability. Like if we have three classes, then it will distribute the probability like first entry 0.2, then second entry 0.7, then third entry 0.1. Then the highest probability for which class? For the second class, which is on one index. So it will return, the second line will return that the highest probability belong to the second class. So it will return us one, the one index. So and again by test label and x is equal to 1 will pick the maximum index across column for each row. X is equal to 1 across column for each row, because in 1 or 10 coding you have seen that for each row we have an array 0 1 0 0. For each row we have tested the maximum across columns. So y test labels will compute the maximum value on the y test, which is already 0 1 0 0. So it will return the one value or two value where is the one. So you have seen here one. So it will return one if one equals one is on the one index. It will return two because one in the third index. So like this, it will return these by test labels and by predicted labels. So now we have done this to ease the computation. Now these two values have the same dimension, like 1 1 or 2 2. What is the class? So we can easily compute what is the accuracy or what is the classification between the classes by this model. So we have imported the classification report comparison matrix. So print classification report, and classification report will take parameters by test labels, by predicted labels, and digit 4 will shows up to 4 decimal places. So it will compute the whole classification report and print it And CM variable will take the confusion matrix for the by-test label and by-predict label. So for this classification report and confusion matrix, it is necessary to convert our predicted values and tested values for the uh, by the probability distribution, by taking the maximum of the probability distribution. So now we have defined the PLT dot figure size is 6.5. And SNS dot heat map will create a heat map. This is called the heat map. So SNS library has the heat map function. So it will create a heat map. CM is the confusion matrix. Confusion matrix and AN not true will provide that these numbers will be shown in this cell. If you do not, if you false here, these numbers will not shown up. And FFT equal to D will take it as integers. So these are the integers in this cells. And CMAP has taken loose. You can also, these are the many CMAPs, reds and different. So you can take, and X-tick labels are range 4. So there are 4 classes. So we have taken range 4, and Y-tick labels also range 4, and PLT dot title and labels are defined it. So this is the classification report. Accuracy is here, precision, recall, F1 score support, and this is the confusion matrix here. So this is for all for the SGD optimizer. Now the same things will be done for the different optimizers. So we will show here that again we will redefine the model. We can take the previous model because it is already trained on SGD. So redefine the model equal to build model. And we have to take SGD with momentum. So optimizer yield SGD learning rate. We defined a different parameter momentum also to take SGD with momentum. And compile again with this optimizer categorical cross entropy and matrix accuracy. And model.fin, we have taken history one here. In previously we have already taken the history. That's why the this variable has changed as history one. So we can in last we can compare all the arrays of history. So model dot fit again train the model and again plot the loss and accuracy. All the things are same here. Just optimizer has changed. Again, we will take the predicted probabilities and maximum of the predicted probability test labels. Again, the classification report. And now you can see by just add up the momentum, the accuracy convergence of the model and provide significant results. And this is the confusion matrix. So this is a better confusion matrix where diagonal values have higher values. So the better confusion matrix can be shown like this, where diagonal entries are higher than the non-diagonal entries. So this is our result for SGD with momentum. And again, AdaGrad from training. So from TensorFlow.keras optimizers, we will import AdaGrad, and AdaGrad already defined in this library. And again, we redefine the model. Again, optimizer, AdaGrad with learning rate. We have taken learning rate same in all these optimizers to see the comparison of this optimizer on the neural network. Again, we will compile the model.fit with history2 variable, and again we will plot it, the accuracy and loss, and again the testing process same for AdaGrad. In AdaGrad also the accuracy is not up to the mark, maybe because of the decaying gradient uh, because of the accumulated gradients. So it is 0.37, and confusion matrix is not as well good. And now we will use RMS prof for training. So again, redefine the model, we'll import the RMS from TensorFlow.keras optimizers. So model again, compile the model, and the fit will train the model. And again, this figure of training loss and training accuracy have seen here. Same things have been done. So for RMS problem, the accuracy is increased and it is 0.89 something, 0.89 something. So these confusion matrix is also good. Then the ADA grade, and using ADAM for training, we have used again TensorFlow.keras optimizers, import ADAM, again model redefined optimizers, all things are same. So using ADAM, the accuracy have increased higher, which is 0.98 on this data set. So ADAM is a predicted very good on trained and also predicted very good as we can see in the classification report with accuracy 0.91, and the confusion matrix is also is good. So compare, we have at last we have seen a comparison plot. That's why we have I defined the history 1, history 2 for this. So it is a dictionary. We have taken laws from all these dictionary, and SGD laws, SGD with momentum laws, label are provided. So here you can see how all these optimizers are trained and how this works on the data set of Mobile Press. So we can see here ADAM and RMS prop is doing good on this data set. It is the training and testing is a task specification. So according, it is based on your data set on your and on your task that which optimizer will provide best results. So here Adam is the most suitable optimizer for every task mostly. So that's why it is doing obviously good, and RMS prop is also doing good. So these are the GD and variance implementation. And now we will move further for the second order method, which is Newton method, which we have studies in the session, in the previous session. So in Newton method, you have studied that it will work better on the quadratic function. So if you remember the mean square error loss, it is a quadratic function. So we will see how neural network in linear regression problems, the mean square error loss will be taken. So on this, the Newton method can work better. So we will see how it will work. So first, we will import the libraries of matplotlib.pyplot, SPLT, pandas, and NumPy. Again, we have taken a data set, which is a salary data set. Using the pandas library, we have created and print the 5 entries. It is outbound teacher ESS salary. So X is take the data ESS experience column of data, and Y is taking the salary column of data. So now we will just a second. So X values, now it is these X is not a NumPy array. So X dot values will convert into a NumPy array, and dot reshape -1 1 will ensure it is a 1D vector. It is in a column vector. So dot reshape -1 1 it convert into a 1D vector, and np dot stack will stack it into that np dot once it will create np dot once will create a vector of x dot shape 0, which are the column of x, and one is the one column, which number of columns. So it will multiply a 1 1 vector with the x values. So x stick with multiplies like it is same as it will take 1 1 1 entry ahead of the uh, years of experience column, and whenever we take w which is the weight matrix, it will multiply it by 1 first, then it will multiply it by the x. That is how it will be done. And the loss function of mean square error, So the XW is the predicted function. X is our input data set. Weights are provided. So XW is the predicted value and Y is the true value. So this is our mean square error. And in mathematical form, XW are now as a column vectors. W is a column vector. Y is also vector. So 1 by 2n. And the gradient will be taken as X transpose XW minus X transpose Y. 1 by n will be divided in gradient of loss function, and 1 by n will be divided. We have taken 1 by 2n to simplicity. Whenever we have we will do derivative of this, 2 will be cut by this 2 and n for the average. So 1 by n also divided in right hand side also it will be divided. So 1 by n h is Hessian, and update step is W new, which W minus Hessian inverse and gradient multiplied. So now we will define a mean square error. Definition of mean square error. By true, by predicted are the parameters. It will return 1 by 2 np dot mean of y true. Y true values are not a numpy array. So y true dot values will create a numpy array. Dot reshape minus 1 1 will create it as a column vector. And y predicted is already a column vector. So now these are convenient to do this subtraction, column matrix subtraction. So it will return us 1 by 2n by 2 minus y predicted to the square. Now we will define a definition of Newton-Linear regression. So input data, y output, tolerance, and maximum iteration 10. So in x dot shape, what is the x dot shape? This is x dot shape is a one-dimensional vector. So obviously the columns are one. So it is n samples which refer to the rows and features for the columns. So samples, the how many rows in this are the number of samples. How many features? It is a there is a one feature only. So it will assign the number of samples and number of features from x dot shape. And W is the weight vector which will initialize by the 0 np dot zeros and feature 1. So it is a weight vector. And mean square error history, it will create an empty, it is an empty array which will add up the mean square error for each updated point by the Newton method in this array. For I in range of maximum iteration, we will take y predicted xw. The at the rate will take the mathematical matrix multiplication in Python. So y predicted x dot w, and MSE mean square error will be what? Mean square error already defined here. So y true, y predicted. So y is already and defined here, but y predicted has here and already defined, and it will be shaped because it will defined in the definition already. So it will compute us the mean square error, and the mean square error for this weight matrix will be appended in the MSE history array. And gradient is 1 by n samples x transpose multiplied by x multiplied by W weight matrix minus x transpose y. And again, y values will be reshaped and into a one-dimensional column vector, and Hessian is x transpose x. So these are the definition. And now we will take the inverse of Hessian. NP dot linear algebra is a library is a function in NumPy library. So dot inverse will take the inverse of Hessian and it will multiply by the gradient. And again, it is the update step. So W is updated now by the Newton method for first epoch, first iteration. And if this thing, the H inverse multiplied by gradient is less than tolerance, like is it tolerance is defined e to 10 to the power minus 6, less than tolerance, then we will print that converge at this iteration. For which iteration it will less than the tolerance, we will print this converge at iteration and the loop will break. So when it will less than 10 to the power minus 6, the updation is very small. That's why we will return it. This definition, Newton linear regression will return us W and MSC history. W is weight matrix, MSC history is an array which will store the every updated W MSC. So now we will call this Newton linear regression definition for W Newton and MSC history. It will return two parameters. So now we will plot the how MSC is decreasing with Newton's method. So MSC is C and marker O has been for the point and color dark blue has taken here. Again, all the things are same for the plot and final prediction and plot for we have taken white. Final W Newton. Finally W Newton is after the training. So we will multiply it by XB and XC is here to remember, which is still here. So XY, it will again plot the fitted line. It will again plot the fitted line on the data set. So it printed converge at iteration 1 because it is a quadratic function. So it will converge at iteration 1 and on in just one iteration, it will converge to the loss 0 for the mean square error. And this is the fitted line Newton by the Newton method. By the final parameters W, it will compute it. So these are the parameters W and V. So that's how the Newton method will work for the quadratic function in implementation. But in real life neural network models, the laws are not quadratic, and if it is very computationally expensive to take out the inverse of Hessian in again and again. So it is not very practically usable, but for smaller tasks we can use it, and in um, sometimes for depend on the data set and loss function, we can use it and try to interpret the results. We can surely get better results for the quadratic loss functions. So uh, this is for the as GD and gradients and the Newton method. Now we will move further for the activation function implementation. So you all have read the activation function in the previous session of today. So we have seen different activation. So in this implementation, we have taken different tasks and different data sets for each activation function, which will beneficial for that particular activation function only. So to show the use of particular activation functions in this implementation. So let's get started with sigmoid function. So experiment 1 will show the sigmoid function used for binary classification. So sigmoid function generally will not use in the hidden layers. It will use in the output layers for the binary classification only. Classification data. See how we will insert the sigmoid function in the model to train binary data by that model. It is the import company by handling new and SQL or machine task or so we can check our optimization approach on this benchmark data set. So breast, am I not audible? Hello, am I not audible?
Yes, you are audible, Rinki ma'am.
Yes. So which will load breast cancer will load the breast cancer benchmark dataset, which is a binary dataset which has the attributes of the breast cancer tumor, and it will based on these features of the breast cancer tumor, it will tell us the tumor is cancerous or non-cancer, which is malignant and benign. So it is a binary output. So and again, sklearn dot model selection will import trend test split, which will split the data set. And from sklearn dot preprocessing, import the standard scaler. Standard scaler will use for normalize the data set. It is a preprocessing tool that standardize features by scaling it to a unit variance. So without scaling, large ranging features can dominate training. That's why. And TensorFlow, STF, Matplotlib. So in data, we will load the breast cancer, and X, Y, we will take the data is this variable. This is object is data, and data is value, data value from this object. So if you can define a different name for this, so that's why it will not create a confusion. Data is whole data by except the target column will insert in X, and data.target, it will show you the difference. It will take the value of target from the data object. It will take the data value from the data object in X or Y. So scalar dot fit transform will be applied on the X data to normalize the data, and again train the it will first create a dense layer of 32 neurons. It is a simple feed-forward neural network, and activation ReLU has been taken, and input layer has the neurons, same as the feature of the data. So X dot shape 1 is the number of columns in the data, which are the number of features. So input layer has the number of neurons, and after that the dense layer of 32 neurons, and after that the 16 neurons dense layer, and to introduce the sigmoid activation in the last layer for the binary classification, we will do this dense one neuron only, and activation equal to sigmoid. So activation equal to sigmoid will directly import the sigmoid activation in the model, and the model dot compile will compile the model with optimize the random loss, binary cross entropy, matrix accuracy, and model dot fit will train the model for 10 epochs. We will train this model for a small number of epochs to just show the how the different activation function will behave for that particular task, and batch size has been taken as 32 per pose 1, and this is for the plotting scenario, and this is the training here. Accuracy has reached up to 0.96. It is a bench it's already, and you can see sigmoid is smoothly, the loss is smoothly converging toward the minimum of minimum loss value. So this is how sigmoid in binary classification can use. And the second experiment is 10 hyperbolic activation function. So mainly 10 hyperbolic activation is used in sentiment analysis and RNN, recurrent neural network, and NLP binary tasks. So you will be this sentiment analysis and NLP will taught in further session of this workshop. So there is a little inference about that. So don't get much complex with this. Just see the inference of that, how NLP, we have taken a simple NLP task to see the use of 10 hyperbolic activation function. So for this, Text sentiment analysis is a classic NLP binary task. And if it is a, what is a sentiment analysis? Like sentiment analysis, we have a, if I provide a review to a movie, it is a negative or a positive. So it is a negative, it is belongs to the 0 class. It is a positive, it is belongs to 1 class. This is the binary NLP task. So that's how why we will take the 10 hyperbolic activation. So 10 hyperbolic is zero-centered and smooth and suitable for recurrent neural network. We have taken recurrent neural network in NLP task because recurrent neural network will take hidden states. It will consider every value in its memory, so it can connect it with the further values. It will connect with the further upcoming values, so it has a memory power. So if I provide a review paragraph, it will connect the first word to the 10th word. That's why we have taken RNN in the NLP task. So 10 hyperbolic has balanced positive and negative signals because it is not biased, because it is a zero-centered. It has output between -1 to 1. So if I have negative input, it will provide the negative output nearer to -1. If I have positive input, it will provide the positive output nearer to 1. So that is the use of 10 hyperbolic 10 hyperbolic function in the NLP task. So here we have imported a benchmark data set on NLP, which is IMDb. It is a movie review data set. It has it has a paragraphs of reviews for each movie by the viewers. So it is in TensorFlow.keras dataset. Is it already uploaded? So we will import it from here, import IMDb, and TensorFlow.keras repository, we will import sequence. So what sequence will do? Sequence words. So it will allow us to take one word at a time and put it in a sequence for to train the RNN. So maximum features have taken 5,000. So because a data set is large, we have for this implementation, we have taken a small maximum feature number 5,000. So only the top 5,000 most frequent words in the dataset vocabulary will be kept, and maximum length of 200. So for every review paragraph, only 200 words will be taken. So after, if any paragraph have, let's take 300 words, then it will truncate to 200, and it will, if it have less than 200, then it's okay. So now we will train that splits the data, and numbers equal to maximum features. So numbers is equal to maximum features means it takes 5,000 most frequent words only, and it will load the data set according to that. So it will load data set according to the 5,000 words only. After the 5,000 words, it will truncate it. So the data set will load accordingly for the train, and sequence.pad sequences will take the extend data set for the maximum length is 200. So it will take the word sequences in a sequence, like first word for the first position, but it will take it in an integer value, because computer understand these mathematical values. So it will take the first word at NGA value and put it in a sequence, the second word at the second place, and the third word in the third place. That's like that. It is sequence. It is called paired sequences of the data. And now the data is ready to fit in the model. So we will create a model by using tf.keras sequential, and uh, embedding layer will turn the word indices into the impose it into the dense 32-dimensional vector. So it will the maximum features are 5,000. It will convert it into a 32-dimensional vector. This layer will convert. First, we will do the embedding of these these feature vector into a 32-dimensional vector. Now it is ready for training for the RNN. So we will load the simple RNN from the tf.keras layers, and 32 neurons will be taken up for this layer, and activation in 10 hyperbolic for to avoid the to take zero-centered output. And because it is a binary data set, so we have taken sigmoid function in the output layer. So model.compile will compile with the ADAM optimizer, and again training and figure, we will plot the figure, and after that we will show training for the 5 number of epochs, and accuracy is reached to the 0.95 because we have taken a small data set from this a small number of features from this data set, maximum feature of 5,000. So that's why in these less number of epochs we have reached up to that much accuracy, and how 10 hyperbolic is smoothly converging to the minimum loss because of the zero-centered policy. So that is for the 10 hyperbolic activation. Now there are 4 functions: ReLU, leaky ReLU, ELU, and switch. These 4 activation functions are mainly suitable on CNN tasks. So we have taken a CNN model on CIFAR10 dataset, which has CIFAR10 dataset has the images of objects of 10 category objects. So it is a 10 class image classification dataset. In this, you also see the use of softmax function for because it's a multi-class classification data set. So we have taken these 4 activation simultaneously in this CNN model. So this is the leaky ReLU, Swiss, and yeah, exponential linear unit ReLU function, and ReLU is maximum of 0s defined here. And, also benchmark data set. We have the which will already imported TensorFlow library, and the 2 categorical will imported. And again we will split the data set by CI for 10.load data will split in 4 parts of explain by 10, explain by test. And this will normalize the pixel values. Pixel value has the range between 0 to 220, 255, and by dividing 255, it will normalize image pixel values between 0 to 1. So it will reduce the computations for the neural network for the CNN, and avoid the diversity in the data. So now we will do one hot encoding for the bytecode. You already have understand the what 2 categorical will do. For the 10 classes, it will, if any member belongs to the class 7, it will provide the one number on the 7th index, and again all numbers will be 0. And activation functions, now we have defined a dictionary of activation functions here. You already familiar with dictionary, we already have used in previous implementation. So ReLU activation function can be directly imported. So it is taken as a string ReLU, and leaky ReLU and ELU will be added as a layer. Like it cannot be implemented directly in a layer as an activation. If we want to apply leaky ReLU and ELU, we have to apply separate layers. And after the data will be output from a dense layer, it will again will be inserted in a activation layer. So it will these 2 functions will behave as a layer separately, and ReLU and switch are activation in the dense layer. It can be inserted in dense layer directly. So these 4 are different functions, and history dictionary to store training histories for the comparison. Dictionary will report for simple key values of activation. It will store the loss values for each activation. And for name activation in activation function dot items. for name activation in activation function dot items will take this is the activation function list more dictionary and it will take the name and activation from here and print the training with activation name will be taken up and as loop. So model with tf.cds taken up and we will first provide input is 32 plus 32 or 32 of the images of CI13 data. So input shape is provided. When image input image shape will be going to the convolution 2D layer which have the 32 filters of 3x3 size. It is a convolution layer. It will add the features of this image and after the activation provided. Activation is provided. Activation layer. The event means that is activation object and this is a class. So if so is a value if is instance of this value is of this class. That means activation is a layer tf.cadus.depth layer. Then we have taken activation directly. If activation is belongs to layer, it will take directly, and else if it is not a layer, it will wrap into a dense layers dot activation, and activation will be taken here. Activation is taken from here. So that's how this loop will do. If it is a layer, it will take directly as activation. If not, it will wrap into a layer with this activation. So we have already defined what is tf.keras.layers in this activation function dictionary. So it will directly take from here. And again, so after this, we have defined max pooling 2D, which is downsamples the feature map from 30 cross 30 and reduce spatial dimensions. And then we have provided flatten layer, which will the image in a matrix form and the feature map, which will flatten the feature map in a one-dimensional vector. And after that, we have a dense layer, which is a fully connected layer, which will train the weight parameters for better accuracy and better training. And again, for this dense layer, we have to apply activation. Again, the activation will apply in the same manner, which I have applied in conventional 2D layer. And because it is a 10 dimensional 10 class data set, so activation equal to softmax will be taken and 10 neuron will be taken in output layer and model will be compiled and history model dot fit will be taken x train y train and epochs are 5 for each activation and the best size and purpose. So it will history dictionary will create it after taking name is in loop here for name. So these all things in the loop for name. So the loop will run for each activation from the dictionary and it will return an array of history for each activation. So this is the training. First, it will run for training with activation loop, training with activation leaky loop for 5 number epochs. And after that, we will plot each name history in history.dictionary items. It will take from that dictionary of loss value. So you can see then on CIF10 data set, it will the leaky ReLU is performing best from all the application functions and also the accuracy is higher for leaky ReLU among the application functions and so if you want any activation function, you can this dot leaky ReLU. If you want dot leaky ReLU, and if you want it, you can take it. If you want the data, and you can direct by the strength value in the workforce. So value in of value and we Optimization function uh, learns the patterns by taking the maximum over multiple linear projections. So max out units are more flexible and can model complex decision boundaries. So we have taken MNIT data set for maxed out because MNIT is a handwritten data set. So which is less clarity because it is we are handwritten and many results are similar like 8 and 9 has not much difference, including features, because there is only a feature of curve, difference of curve like 5. Because max out learns the maximum over the multiple linear projections. That's why it has the benefit of the intra-class variation. Like it can vary it between classes effectively than other activation functions. So max out is important. So we have to this we have this library. So MNIST images are completed first 20 decided. So we have to meet the interior and input expectations from this. So this slide will function. It will take number of it will take the number of units and pieces as the parameters. So number of output neurons in a layer are units and number of linear functions per unit, which will take per maximum of the linear combination are pieces. So we will define these two parameters for the max out definition, max out function, and in max out class there are different definitions of creating unit pieces, weight matrix, bias matrix. So self is the refers to the current object. So self dot units is belongs to the class max out only, and self dot pieces belong to the class max out only. That's why we have used self in class in Python. So and the second definition class max out are build. So it will take input shape and build the weight matrix. So self dot kernel refers to the weight matrix, and self dot add weight, it will add these things in the self dot kernel. So shape is input shape minus 1. So number of input features, input shape minus 1 will take number of input features, and self dot units will be multiplied by the self dot pieces, like self dot pieces, like units of 3 and pieces of 2, then and features of 10, and it will create the weight matrix of shape 10, 6. And then it will compatibilize the weight matrix as second Dora which is a standard and the label is true, so that this weight matrix again, the bias will be created in the same manner because bias is a vector, so it will take on units and pieces as multiplication, and bias will initialize by 0, and it is also variable. So after that, the call definition is taking input only, and which is WX plus B will computed by that, and it will take shape equal to -1 units self pieces. So this shape, what will do the shape that first we have shape of W is 10,6, which I had an example 10,6. Then Z has also the shape of 10,6, but this shape will reshape it into 10. Units are 3, 10, 3, 2. 10 are the best size here. So 10, 3, 2. It will convert into, reshape it to the Z between 10, 3, 2. It will partial, it will differentiate the units and pieces in the shape. So now Z has reshaped, then it will return the maximum of the maximum of the WX plus B transformation, X is equal to -1, X is equal to -1 will take to the maximum across rows. So if we have four pieces, so we have four transformation and we have we have maximum out of it. So we have to take maximum pieces. So we have the next entry is it will take the max. So take only of is 10 and which is units because it has taken the maximum across pieces. That's how the max out function will work activation. And now we will call them, we will create a model using sequential and tf.keras flatten will convert our input image into a one-dimensional layer. We have not used CNN here for image. We will create a simple feed-forward header by converting these images into a one-dimensional vector, and we have called max out for 128 units and 4 pieces here, because in max out we have two parameters, units and pieces. And the last layer is input tf.keras.layers.dense 10 activation is softmax. And model dot compile is taken for the compile the learning mechanism of the model. Optimizer is added and loss is categorical loss entropy, same like before. And model dot fit on extreme y z if books are fine, size. So by taking this out, because it is highly advantageous to that type of MNIC data, in just a 5 years of books, we have reached to the 99 accuracy of training. It is how is converging to the training of the loss. So the loss, this is of the so this is the use of maxed out activation. You can use it according to your data. And the fifth number of experiment of the soft plus activation. So soft plus activation function is for the smoothing the gradient. So if we have real life data sets like real life images which is not as benchmark, so then we have the training is not as smooth, but so we can use soft plus there. So we have taken a real life data set of X-ray images of pneumonia here, and apply the soft plus activation in the training of that and see the advantage of the soft plus here. So again, same thing, rescale pixel values to the range and images, uniform size, and generate batches. And we have first we have import the image data generator. Image data generation generated in TensorFlow, you provides the utilization for image. It will take the images from a directory. It can do augmentation. It can flip your image. Provides shift ranges and all. And so image data generator is the one tool you can use for an image data using the TensorFlow Keras library. So we have defined image height and image width here, best size, and we will define train data gen variable. We will image data generator will rescale the all images between the pixel values of 0 to 1 only. And train data gen has image data generation, so it will take the images from this directory. So the file will provided to you, and this file loaded in my drive. So whenever you run this cell, this content drive, the drive option will be opt out here and down to the sample data. Then you can choose that file and copy the path and just paste it here. Just paste it here for the directory path. And you can also upload all the files from this icon, which will be provided to you for the course. So that's how we can upload our data, and the height size will be taken this, and best size and password is taken. So how these data belongs to this is the product is and software activation is this. And software activation produce more smoother loss useful in medical image classification tasks. Again, we have imported the blank here to send the layers one after another. First, we will create the convolution to the layer with activation ReLU, which will have 32 filters of 3x3 size, and input shape is defined here for that image. So this input image will be go through the 32 the filters of 3x3 size. This will extend the features of this image, and max pooling 2D of 2x2 will reduce the dimension of the feature samples. And after that, it will again go through the second convolution block, which will again extract the important features from this feature maps with activation ReLU and max pooling 2D with again reduce the dimension. So in convolutional layers, the ReLU is perfect. So we have taken the ReLU here. So the gradients are mainly the oscillating gradient are mainly causing in the dense layers. So that's why softness is beneficial in the dense layers only. So we are using softness in the dense layers, and flatten with convert the feature maps into a one-dimensional vector, and dense 128 activation softness will be taken with 128 neurons, and then 64 again second dense layer with activation softness, and the output layer, because it's a binary data, so one, and activation is sigmoid. And so the model dot compile will create the model for with optimizer ADA and loss and metrics and return model. So whenever we call the build CNN model, this definition, it will fit build a model on train generator is defined here. If you remember, train generator. So on the train, it is a train data set. It is defined for 10 epochs. So it will run on this. It will train. So it will and import matplotlib and see the plot of loss. So it has oscillation, but it is smoother than gradients and is really converging to the minimum software. We can use a software activation like this in our model. So that is all for the activation functions and all these things which are covered today. If you have any doubt, you can ask me.
So please share the files so that can be shared. Actually, there was a lot of sound issues. So I think sharing the